Hey everyone, Chang here and welcome to my channel. Today I'm going to talk about a common scenario that actually each and every one of us has encountered before. It's one of those situations where we look at a problem or presented a situation and we immediately think that we know the answer right away, answered it, and then afterwards all your friends look at you like you're some kind of idiot. You sit there and be like, what? What happened? Think about it. And all of a sudden you're like, oh my God, I'm such an idiot. How can I get those wrong? Right? That's the type of problem that I'm going to talk about today. And they're basically very easy counting problems that ends up being extremely difficult. Here's a classic example right here. Now, a teacher assigns you problems number 10 all the way to number 30. How many problems do you have to do, right? Well, I mean, don't be a smart aleck like, oh, I don't have to do any problem because, okay. Imagine you're just answering this question. Immediately you jump, all right, so 30 problems and then 10 problems. So all I have to do is 30 minus 10 and I get the correct answer, right? 30 minus 10 is 20. No, that's one of those moments where you're like, oh, I'm such an idiot. Why is that, right? It's so simple and complicated at the same time. 30 minus 10 should equal 20. But that's not the correct answer. The correct answer is actually 21. How? Well, let's think of it this way. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Why is that 11? And if we count all those numbers, there's actually 10 right here. There's 10 numbers right here, right? And then there's 11 numbers right here. So when you add these two together, there's actually 21. The reason is because we forgot to include the 10, right? We think immediately, all right, 10 and 30, we subtracted 20, that's fine. But when you get 30 and you subtract 10, you're actually counting 20 problems starting from 11, 12, 13, 14, so on and so forth, right? Just think of it this way. If I asked you to count all the numbers from 0 to 10, although immediately we want to think there's 10 numbers, we need to take into consideration the 0. So that's the situation that I want to bring into focus today. There's these kind of problems where we forget to count a number when we should have. And there's another one, which I'm going to show you in a bit, where we accidentally count a number when we shouldn't. Alright, so for this problem, as I mentioned, it's one where we might accidentally count numbers when we really shouldn't have. So Bob starts at the number 75 and continue counting by 5. What is the 15th term? Immediately, well, I mean, if you're counting by 5, that means you're adding 5 every time. If you're going all the way to the 15th term, all you have to do is get 5 times 15. Well, let's do that. 15 times 5, what is that? Well, 5 times 5 is 25, and then technically the 10, right? Times 5 is 50, so 25, 50, that's 75, right? And then so with that, what else? We have to add it to the original 75, so 75 plus 75, that is 150. So the 15th term is 150, correct? No, it's not. Sad to say, right? So this one, if we go by this method, then yes, we're including a number that we shouldn't. Remember that we started off at 75. 100, what is that? 1, 2, 3, 4, 5, 6, and then we keep going, right? And then afterwards, if we keep counting, so 100, and then 105, and then 110, 115, 120, 25, 130, 135, 140, 145, right? And then so on and so forth. Well, actually, the number is 145. Why is that? Because when we multiply by 15, right, we are assuming that we're adding 15 times, but we're not. We're looking for the 15th term. Technically, this is our first term. So in order to get to the 15th term, we actually have to only add 5 14 times. Hence, if we just immediately assume 15 times 5, we overcount it. So the actual thing is going to be 14 times 5, which is actually 70. So with the original number, your first term, you're going to add 70. So it's going to be 75 plus 70, which is actually 145. So the actual answer is 145. So this situation, well, overcount, right? The first situation, undercount. So what do we do in, I guess, to avoid situations like that? All right, so with that, we actually have two situations, right? There's one where we undercount, right? We miss something that we should have counted. And there's the other, like this, where we overcount it, right? We counted something that actually technically shouldn't have been counted because, I mean, that was, in this case, the original term. That was the original first term. There was no zero term. So technically, you only count to 14 instead of 15. Now, how do we avoid falling for those kind of mistakes? As much as I want to say there is an easy way to always just check, there really isn't, right? We have to actually really think about it. For each and every one of the problem, the question we really have to ask ourselves is the first term included or excluded? Is the last term included or excluded, right? If we can always ask ourselves that, usually, I don't want to say 100%, but about 95% of the time, you're probably going to be fine because as you can see from these situations, usually the miscounting comes from either the first or the last term. So every time you encounter a problem, especially one where your gut instinct in relation to counting is like, I immediately know to add, subtract, multiply, whatsoever, ask yourself the question, is the beginning term included in my calculation? Is it supposed to be included? Is the ending term included? Is it supposed to be included? And just by asking yourself a question like that, you can actually maybe prevent a good number of these mistakes. So let's look at more common problems that would potentially lead to them or these kind of error, and then let's work through it and see what happens. Now here's another problem that sort of dupes a lot of people. Now, we have a square, which is a 1 foot by 1 foot, and usually similar problems are some square or rectangle, and they have some way of including either dots or fence posts or whatsoever. But basically, there is a dot on every inch. How many dots are there total? Well, if we remember correctly, 1 foot is equal to 12 inches. Equals 12 inch, which is not bad, right? And afterwards, well, if there's 12 here, 12 here, 12 here, and 12 here, that's technically 4 sides of a square. So it's going to be 4 times 12, and we know that each inch is going to have a dot. So that's going to give us 48, right? 48 dots total. Now, that kind of reasoning makes absolute sense. The only problem is that it's incorrect. There's a reason for that, right? When we look this way, there's going to be 12. When we look this way, there's going to be 12. When we look this way, there's also going to be 12. And we look this way, 12 again. So why is it that even though we say 48, there's actually not a total of 48 dots? I'm going to give you the answer actually right away. 44 dots is the correct answer. And we can actually check this is because if we ask ourselves, what are included and what is excluded? Are we overcounting or undercounting? Well, on the top side, imagine there are 12 dots, right? That's cool. On this side, we also have 12 dots. But if we look at both of them at the same time, notice this. This row of dots, or I mean, this is a line, but technically the row of dots here, this 12 and this 12, share one right in that corner. By that same reasoning, this 12 and this 12 shares this one right there, right? And same here. Here shares that little corner right there, and the same right here. So what happens is that even if we're looking from all these sides, there are 12. Yes, individually they're 12, but if we're starting to count all of them together, we accidentally count these guys more than once, right? Because if we count this one, all right, here's 12, but they're sharing that same dot, right? Here's 12 sharing that same dot. Here's 12 sharing that and that. So instead of the standard 48 that we automatically would assume, technically it's 44, right? We're overcounting these dots right there. Now this problem right here, I actually really like it just because of how simplistic it is in terms of the way it asks, right? Even though it's a weirdly phrased question, it gives you all the detail needed to actually solve this problem. How many two-digit whole numbers are there? Well, actually, that's quite simple. Two-digit whole numbers are basically all the numbers from 10 to 99, right? Anything less, we don't want. Anything greater, we don't want, right? Because anything less is just 1 digit. Anything greater is 3 digit. So all we have to do is just figure out the difference, right? 99 and 10. How many numbers are there total? Well, once again, the common mistake could be just, well, if I do 99 minus 10, that gives me 89. Not so great. So let's just figure out, just by trying to reason it out, what we can do. Well, let's just use something that we're so comfortable with. 1 to 100, right? The numbers 1 to 100. Well, okay, there's a total of 100 numbers here. Cool. But there's some numbers that we don't want to include because we're only focusing on the 2-digit whole numbers. So that's a total of 9 numbers we want to get rid of. So 100 numbers minus 9 numbers is 91. We're done, right? No, not necessarily, because even though we got rid of all the single digits, remember, the numbers 1 to 100, that gives us 100 numbers, right? There's still one more number we really don't want. That guy, right? That's a 3-digit number, so that's only, luckily, one 3-digit number, right? So that's one more number that we want to get rid of. So in that case, instead of 91, subtract one more, 90. And so our answer for this one is actually 90 numbers total, not 89 that we would automatically assume if we just saw this 10 to 99, right? So we have to be careful. Once again, are we overcounting? Are we undercounting? In this case, we would have undercounted, right? We would have been clearly missing one number. Alright, so for this problem, this is one that I would normally write for my students if I really want to create a problem that emphasizes counting numbers, what should be counted, what should not be counted, are you over counting, under counting? This is the type of problem that I would write, right? How many numbers less than 100 are multiples of 3 but not 2? Now here's the thing, of course if it's less than 100, great. Anything greater than 100, then we're working with really big numbers. So luckily this problem is designed so that is not the case. Well, here's the thing, we want it to be multiples of 3. 3 times 1, 3 times 2, 3 times 3, so on and so forth. Now, the best way to limit this is to figure out what is the largest number that is a multiple of 3, but it's less than 100. Well, from our experience, it's fairly simple. 99. 99, if I divide it by 3, that's going to give us 33. What's significant about 33? That means that, well, from 3 times 1 to 3 times 2 to 3 times 3 to 3 times 4, so on and so forth, it can go all the way until 3 times 33. Because that gives us 99. Any more than that and we exceed 100 and we don't care about that. So technically there's a total of 33 numbers that are multiples of 3. Multiples of 3. Okay? Well, normally we would be done. We'd be great. But not 2, meaning not a multiple of 2. So, in that case, in this 33 number, there are some that are going to be multiples of 3 and 2, and we don't want that, well, based on the problem. So what we have to do is figure out what they are and get rid of them. Well, this is what makes this a good problem. A lot of the problems that you guys are going to encounter is not going to be specifically focused only on one topic. I mean, there are some problems that are designed that way, but what makes this a good problem is that it takes a lot of different topics and then put it together to make one solid problem. So, multiples of 3 and 2 relies on sort of the divisibility rules. To find out if a number is multiple of 3 and 2, well, that means it has to be a multiple of 6, right? 3 times 2 is 6. So, as long as we can find all the numbers that are multiples of 6, that's less than 100, and we get rid of them from the multiples of 3, then we're good to go. So, we have to figure out what's the largest number that's less than 100 that is a multiple of 6. In this case, it's actually 96. Alright, 96, because 97, 98, 99, and then, of course, not 100. But you can test them out. But 96, I believe, is the biggest number that's divisible by 6. Well, here you go. Divide by 6. 6 goes in here how many times? 1, and then that's 36. So that's going to be 16. There's 16 numbers total. So, total of 16 numbers are multiples of 3 and 2. 3 and 2. Okay, so out of 33, there's 16 of them that are multiples of 3 and 2. So as long as we can get 33 and then subtract 16, right? that will give us our true number, which is 17. So the total numbers that are less than 100 and are multiples of 3, but not 2, is actually 17. And so, with the end of this problem, well, hopefully you guys can see why I like this problem so much, right? You can count them, especially if you have 1 to 100 right in front of you. But this one takes a lot of like sort of reason out. Did I overcount? Did I undercount? I did, right? With 33 numbers, I overcounted because I didn't want these guys. Now I just had to figure out what I overcounted and get rid of them. Now, so hopefully with all these problems, you guys can see that even though counting seems kind of like such a basic thing, there can be complex situation. And it's complex not because it's completely difficult, but because it opens so much room for accidentally overcounting and undercounting. Now, with these, I really want to emphasize that just make sure you walk through the problem. Always ask yourself, what numbers are included? What numbers are excluded? What did I accidentally include? What did I accidentally exclude? Because those are the ones that always causes trouble. Some of them are in the beginning, some of them are overlapping. That's the key, right? Certain things are overlapping and you might overcount. Certain things are not overlapping that we thought are overlapping and we undercount. So hopefully this video, with just the numerous practice that I crammed in here, that we become a little more aware. And just by becoming a little more aware, then we can prevent a lot of these mistakes. Thank you for watching this video. See you in the next one.